Hi everyone. This is the Early Child Development and Learning session. We have Professors Elizabeth Spelke from Harvard, and Professor Singh from the Department of Physiology. And the chair for the session will be Professor George Augustine.
Morning, everyone. I'd like to welcome you to our session on early child development. Every parent is deeply impressed by the myriad of profound behavioral changes that occur as a child matures. It goes without saying that this process of child development is a fundamentally important topic for all societies, particularly in Singapore, where children receive intensive educational training from a relatively early age. Scientific research on early child development, such as what we will hear in this morning's session, can help us to improve learning strategies to enhance individual creativity and leadership potential. It can also aid us in helping children with developmental-related disabilities. For the students in the audience, today's talks are also important because they can offer ways to improve your own personal learning strategies, as well as providing information about possible career options in this field. So like everyone else in our audience, I'm excited to hear what today's authorities on early child development have to tell us about their latest research findings. My main role as chair of this session is to introduce our two featured speakers, and it's my great pleasure to first introduce our keynote speaker, Professor Elizabeth Spelke. Professor Spelke is on the faculty at Harvard University, and she studies infants and children to identify the sources of cognitive capacities that are unique to humans. Her signature idea is that babies are born equipped with certain basic capabilities for ordering their world. Professor Spelke has been a phenomenally productive researcher, and as a result has received numerous honors, including being a member of the United States National Academy of Sciences, a fellow of the American Association for the Advancement of Science, and member of the American Academy of Arts and Sciences. Her pursuits entered the public domain in large part due to her reaction to the proposal of Harvard President Larry Summers that women have been less successful in science and engineering because of differences in their intrinsic intellectual abilities. This led to a famous debate between Professor Spelke and Professor Steven Pinker at Harvard that hopefully defused Summers' infamous proposal. As a result of the popular appeal of her work and her ideas, she surely must be the only speaker at CogSci Cadex whose work has been featured not only in scientific scholarly journals, but also in popular magazines such as Time and The New Yorker. Without further ado, I would like to welcome Professor Spelke, who will speak to us about core knowledge and cognitive development, the case of geometry.
Okay, great. So, yesterday, we heard at this wonderful meeting, and thank you, let me add my voice to thank Tara and all of you for that, about three compelling reasons why cognitive science is a great field to think about and maybe to enter. One, that it's extremely interdisciplinary. Two, that it is asking questions that are some of the most interesting questions in the world about the most interesting object in the world, namely us. And three, that the answers to those questions have great importance for human health and human education and human society and a bunch of other things. Now, I believe that all of those points are true and hope to touch on them in my talk today. But what I want to focus on is what I think are three other great things about cognitive science. And here they are. First of all, cognitive science addresses some of the oldest and thorniest and greatest questions that human minds have ever confronted. And in particular, here are three of them. One, what's special about human cognition? When we compare our perceptual capacities or our action capacities to those of other animals, we see enormous similarities. But when we then ask, what do we do with these capacities? What do we do to the world around us? What do we do to ourselves and our own concepts? What kinds of objects and institutions and social relationships do we develop? We see an enormous gap between us and every other living being on the planet. And that raises the question, what's the source of that difference? What is it about us and about human nature that allows us to take these capacities that we share with other animals and move them into so many diverse new territories? The second question, a great old question, is where do abstract ideas come from? If you look at all of the intellectual pursuits that humans have been able to develop, the sorts of things that get represented at universities like NUS, you see at the center of them a set of concepts that refer to entities that you can't see, that you can't grasp, that you can't point to and communicate about directly with other people, and yet that are absolutely fundamental to the development of everything that we do, from moral systems to economics to science and mathematics. So how are we able to think these thoughts, and how are we able to convey them to other people, especially to the young during education? And then the final question, it seems quite obvious and must be obvious to any educator that when we learn new things, we do so by building on what we already know. Now, what this should naturally tend to produce is an expansion of knowledge that retains the initial knowledge. But one thing that seems to happen again and again, both in the history of science and mathematics, but also in ordinary cognitive development and everyday education, is that we use what we know to discover that what we know is wrong, or too limited, or not powerful enough, and we go beyond those initial concepts. How is it that we're able to do that? So these are the kinds of questions that you're going to bump up against again and again if you pursue research in cognitive science. I think questions like this animate a whole lot of the activity that you hear about in meetings like this. Now, the second thing that I think is great, that I want to add to the list of things that are great about cognitive science, is that it's a very young field and it's making rapid progress. And in particular, I think it's making progress on all of these old questions by narrowing the field of possible answers to us and giving us partial insights into them. But the third, and I think the best great thing about cognitive science is that it has not answered these questions yet. These questions are still outstanding, which means if you want to go into a field where you're going to be dotting I's and crossing T's and appending footnotes to some field of knowledge, this is not the field for you. This is a field for people who want to take fundamental questions and gain fundamental insight into them. And what I would like to try to convince you of today is that although we haven't gotten there yet on these 2,000-year-old, ancient, very hard questions, I think we're poised to be able to answer them. Probably not in my generation, but probably, I think, in yours. So this is a field I would invite you to go into if you want to take on big challenges like these. Okay, now those are grand things to try to convince you of. What I'm going to actually do is take a single example of research. And I found myself regretting over the course of dinner last night and thinking about this talk today that I couldn't tell you about some of the areas of research that are of immediate practical significance and interest. I'm not going to say anything about gender in science. I'm actually not going to say anything about number and development of symbolic mathematics, which is something that I've worked on, or social cognition, which I've also worked on. I just want to focus on one area and use it as a way of trying to show you how cognitive science is working to make progress on these big questions. And the area is the whole set of concepts of Euclidean plane geometry that center on points and lines and geometrical figures and their properties. And I choose this set of concepts for a couple of reasons. First of all, the concepts of Euclidean geometry have been critical throughout human history to almost everything that we do, from discovering ways to measure time and space to the development of the sciences and the arts and fields like mathematics. Second, Euclidean geometry is an extremely simple system. As Euclid showed more than 2 millennia ago, you can capture all of the basic properties of points and lines and figures with just 5 postulates and a few rules of logic. Compared to all of our other abstract concepts, this looks like a very simple system. Now, all of the Euclidean concepts are abstract. If you're interested in abstract ideas, then thinking about points and lines are really interesting things to think about because, of course, a point is so small it has no dimensionality. It's something that not only no living being could ever see, but no physical device could ever detect. When we reason about them, we're reasoning about something that goes radically below the resolution of anything that we could experience. But of course, Euclidean objects are also bigger than anything that we could experience, like lines that never end and so forth. So they outrun our experience in some pretty clear and obvious ways. Also, Euclidean geometry is a parade case of a system that while it's extremely useful to us, we've also been able to discover its limitations. Discover that there are other geometries that are more powerful, more general, and provide better descriptions of the world. So it's a nice case. I won't have too much to say about this, but I think going forward it'll be a very nice case to look at to try to see how we go beyond our initial concepts. Now, another thing that's great about Euclidean geometry is it's been studied for a very long time. We've got lots of information about it. One of the first studies in proto-cognitive science, one of the first experiments ever done by a human being on human nature and human knowledge, was reported by Plato in the Meno. It's the study in which Socrates, asking the question about abstract concepts, how is it possible to have an abstract concept, showed that he could take a completely uneducated slave and simply by asking questions, not by feeding the slave any answers, just asking the questions, get the slave to discover rather fancy, sophisticated properties of points and lines and figures, like that the area of a square doubles in proportion to the square root of the length, the square root of 2 times the length of one of its sides. So interesting, and if you haven't read this dialogue in the Meno, I highly recommend it to you. Very interesting early study of knowledge of geometry. Now, before Helmholtz, who Brian Scholl told you about yesterday, there was Descartes, who showed in the 17th century that you could use basic principles of geometry and appeal to basic representations of geometry in human beings to understand things like what Helmholtz came to call unconscious inference, how in vision we go beyond what's immediately available to us. For about 100 years, people have been studying the behavior of animals in natural situations, and studies of spatial behavior, like how animals find their way from one place to another, have figured in these studies since the very beginning. If you want to read just one beautiful example, read Steve Emlin's studies of how birds figure out the first time they migrate what the direction of south is by learning and then analyzing the geometrical structure of the stars in the sky. And within the field, the history of experimental psychology, people have been studying rats, learning their way around places like mazes in order to understand basic properties of learning and memory and representation. And finally, analysis of geometric properties has been fundamental to the growth of neuroscience, which is, of course, also a major thread within cognitive science. In particular, the beautiful studies that have shed light on the nature and organization of the brain in general, as well as the visual system in particular, by looking at how individual neurons change their response properties as you vary simple geometric properties of the world, like the orientation of a line or the nature of a junction where 2 lines meet. So there's all this rich work out there, and yet the most basic questions are still open and up for grabs. What are the sources of these Euclidean geometrical intuitions that all the people who did this research had, and that was guiding their research, and that they're imputing in one way or another to the people who they're studying? And how do we develop them? So what I want to do today, because these questions are still open, is focus them somewhat for you by telling you about some lines of research that are ongoing or have been done recently. And I want to start with a study in the spirit of Socrates